Hello, in this video I will be deriving an equation to calculate the reverberation time inside the room. I will assume that the sound field inside the room is homogeneous. Let me start by using the small volume dV shown in the diagram. The small volume dV has the sides dr, r d theta and r sine theta d phi. Therefore, dV is equal to r squared times sine theta times d theta times d phi times dr. The small volume dV is radiating sound energy equally in all directions with velocity c. Therefore, the amount of differential sound energy striking an elementary small surface area ds is given by dE equals to dV times E sub d times ds times cos theta times 1 over 4 pi r squared. And the terms of this equation are explained below. Now, substituting for dV from above into the equation for dE gives the following expressions. The total differential amount of sound energy contributing to ds of a hemispherical shell of radius r and thickness dr is given by the following expression. And after the manipulation of this expression, we obtain an expression for the total differential amount of sound energy, which is dE equals 1 over 4 times E sub d times ds times dr. But this total differential amount of sound energy propagates towards the small boundary area ds with velocity c, where c is equal to dr over dt. Therefore, the rate at which the sound energy arrives at ds is given by dE over dt equals 1 over 4 times E sub d times ds times dr over dt, which is the acoustic power in joules per second. The acoustic intensity is defined as the amount of acoustic power passing through a unit area that is perpendicular to the direction of sound propagation. Therefore, the acoustic intensity is equal to V times dE sub d over dt divided by ds, which can be written as I equals C times E sub d over 4. This is the intensity of the diffuse field sound energy at the room boundaries. Now, if the room has wall areas S1, S2, all the way up to Sn, with corresponding average sound absorption coefficients alpha 1, alpha 2, all the way up to alpha n, then the rate at which the sound energy absorbed by all room wall surfaces can be expressed as a sum as follows. And we can write I times A equals C times A times E sub d divided by 4. Now, dividing both sides of this equation by the room volume and the sound energy density gives the following expression, where tau sub E is equal to 4 times V over C times A in seconds. The growth of sound energy in a room can be modeled using the following statement. Sound power input is equal to the rate of sound energy growth plus the amount of sound energy absorbed. The above statement can be expressed as a first-order differential equation governing the growth of sound energy inside the room as follows. Using this energy balance equation, it will be possible to look at the following two situations. First, let me consider the case where a steady sound source has been on for a long enough time, resulting in the sound source input to reach its equilibrium inside the room. When this occurs, the rate of change of the sound energy density, dE sub d over dt, is equal to 0, and the sound energy balance equation reduces to capital Pi is equal to C times A times E sub d divided by 4. On the other hand, if the sound power input is turned off, the first order differential equation will become homogeneous, as the sound power input is zero. It would then be possible to use the solution of this homogeneous first order differential equation to obtain an equation for the reverberation time of a room. So, in this case, the first order differential equation becomes 0 equals V times d E sub d over dt plus C times A times E sub d over 4. After rearranging and integrating it, we have natural logarithm of E sub d equals negative t over tau sub e plus C1, where C1 is the integration constant to be found. And after further manipulation of this expression, we have E sub d equals C times e raised to the power minus t over tau sub e. And using the initial condition that at t equals 0 second, we represent the total sound energy in the room just after the sound source is turned off by E naught, we find that C is equal to E naught. Now, substituting E naught for C in the equation for E sub d gives E sub d is equal to E naught times e raised to the power negative t over tau sub e, where E naught is the initial sound energy density inside the room at t equals 0 seconds and is assumed to be the same throughout. The reverberation time is defined as the time taken for the sound energy density to drop to 1/millionth of its initial value, and this corresponds to a 60 dB reduction. Therefore, setting E sub d over E naught equals 10 to the power of minus 6, we get 10 to the power of minus 6 is equal to e raised to the power negative t over tau sub e. And after manipulating this expression, we arrived at an expression for t, which is equal to 55.262 times v over c times a. Now, taking the speed of sound in air at 20 degrees centigrade as c equals 343.5 meters per second, we can write t is equal to 0.161 times v over a in seconds. And by replacing the subject t with t sub 60 to represent the reverberation time, we can write the above equation as follows. This reverberation time equation is known as the Sabine's reverberation time formula, as it was developed as a result of Wallis-Clement Sabine's investigations conducted around 1895 while he was an assistant physics professor at Harvard University, and when he was given the task of improving the folk lecture hall of the university. Reverberation time is considered to be the most important single quantity that provides information on the acoustic quality of a room, and Sabine's formula is widely used in guidance documents and international standards relating to room acoustics. This brings me to the end of this video, and I hope that you have found this video useful. Thank you for watching.